I'm absolutely a big fan.
Some girl died from it, no? For charged lemonade. I saw.
Yeah, there should be like a warning, like must be strong.
They add that, yeah. It's like
It's not for the weed.
it's something. All right, let's get started. Hey guys, thank you for being here today. Discussion 7, basics on GPU programming using CUDA. So before we get started, who here has learned CUDA or has done GPU programming before? No one? Okay. Yeah, that's fine. Honestly, this discussion will serve you good for your next assignment, which involves GPU programming with CUDA. So yeah, let's get started. The overview of today is basically the core idea of what GPU programming is and why we do it using CUDA, and then the overall differences between GPUs and CPUs, right? And we'll be going over a basic skeleton example of a program, and then we go through each function and see what purpose they serve in the overall program space. And then I'll be going over some kernel configurations. So what are grids, blocks? These are some things that are really important, and threads, okay? So the goal of this discussion is, if there's anything I want you guys to take away from, is what is a grid and what is a block and what purpose they serve in CUDA programming, okay? Those are two things that I want you guys to really nail down, basically. Okay, so the basic intuition of CUDA, as well as just what it is we launch what we call multiple threads in groups of thread blocks to form a grid, okay? This might seem a mouthful, but the basic intuition is this. Let's say you have two arrays, right? You have array one and array 2. And let's say you want to add the values in the second one to those to the first one, okay? In basic C++, you'd actually just use a for loop, right? So you iterate through each value and perform a sum, okay? So this is fine, but in CUDA, the beauty of it is that it gives us what we call threads. So in CUDA, we create 6 threads, and each thread will take care of a single operation. So in this case, a single addition, and they will run everything concurrently at the same time, like this, right? So in CUDA, instead of just going through a for loop, you actually instantiate all these threads to perform one operation, one function that we call a kernel. We'll look into that in a bit. So what are the core benefits, right? So the whole point of a GPU is the fact that in reality, you won't have access to hundreds and thousands of CPUs to run a problem. If you do have access to that, then that's good for you. But in general, a GPU can take care of that by giving you hundreds and thousands of threads that could perform a single operation at the same time. And you launch what we call a kernel. So a kernel is basically, you can just view as a function in GPU programming. And there's a special syntax which dictates how many threads are specified in each kernel and which configurations we can run specifically, okay? And these are void functions, so they return nothing. And there's some limitations with regards of recursion, so that's not something you really want to do using kernels, all right? Any questions? Cool. Yeah.
So you said like recursion is recommended?
No, not recommended.
No.
Yeah, not recommended. Yeah, you don't want to do that. I didn't say that. All right. So GPU memory is not the same as CPU memory, okay? So most of your programs do run on CPUs, and in GPU programming terminology, we call the CPU the host, okay? And the GPU is called the device. And the device cannot see the system RAM of the host. And these days, the biggest bottlenecks in GPU programming, it doesn't really involve specifically regarding the GPU architecture. It actually involves the performance of the GPU that transfers the data between the host and the device. So whenever you transfer the data from host to device and back and forth, that operation is very expensive. And that's where you get the bottlenecks of different GPUs, okay? So the overall structure of CUDA, or just GPU programming, you start by initializing the data on the host, right? Once you've done that, you allocate enough memory on the device, you move it from host to device, you launch the kernel, which is your main function to perform the operation, and then the GPU calculates the results on device. And once that's done, you need to move that result back onto your main program to use it, okay? And this will become more evident as we go through different examples. Cool? Oh, these slides and code should be on Canvas right now. Yeah. So, sorry. So in CUDA programs, we have 3 types of functions, all right? And these are marked by qualifiers. You have global, device, and host. So global, that's just called by the host and it will run on device. The device qualifier is called by the device, and it you can view it as a helper function for your kernel, and it really helps with abstractions as you go into more complex programming. And lastly, you have the host function. That's just, you don't really need to put it in front of your function. It's just for your normal like main function, for instance, that's your host function, okay? Now, as I said, the typical flow of CUDA programs is this structure. Just remember this whenever you're doing your next assignment. So you initialize the data on the host, you allocate the memory for copies of data on the device, you copy the data to device, and we'll look at the functions that you need to do that. You launch a kernel function to perform operations, right? That's your basic function that you're using. And you copy your results back to host memory. And most importantly, and this is where I think many students will just forget to do, is you have to freely allocate the device memory. So if you don't do that, you'll just end up with garbage outputs or just multiple errors that you won't be able to decipher. So please do not forget to freely allocate, like free your memory at the end, okay? Now, here are some useful functions that you'll be using, just in general. I'll skip this for now. This is just in the slides for reference when you do your assignment, but we'll go through each function in the coding example in a bit, okay? So you have like CUDA malloc, CUDA free, and then CUDA memcopy, all right? Now, the fun part, launching a kernel. So the last thing I want you guys to look at before the example program is the general syntax of how do you launch a kernel function. So as I said, a kernel function is just the basic function that performs the operation that you need. In this case, we specify the kernel function as kernel name. So that's just the name of your function. Then between the three chevrons, you have grid dim and block dim, okay? Now, and after that, you specify the different parameters that you need. So what's happening between the three chevrons is that, so grid shape, okay, which is grid dim, it specifies how many grids there are and what shape these grids are. And then conversely, block dim specifies how many threads are included and what shape are in each block, okay? Now, it's okay if this doesn't mean anything to you right now, but the later problems that we'll look at will make it more evident as to what these mean and how that is influenced by the GPU architecture in general, okay? Now, the fun time. So there's an example on Canvas right now for example.CUDA. Basically, what it does is initializes two integers on the host, okay? And then it copies the integers to device memory. It calls the kernel that adds the integers together. You should see it add one. And then, sorry, the sum function. It copies the sum back to host memory, prints the sum out, and then freely allocates the device memory, all right? So I want you guys to take 5 minutes to try to run this example on Great Lakes right now. So just remember that before you run anything with CUDA, make sure you module load CUDA, okay? And once you've done that, compile using EECS, okay? And then you submit the batch file as it is, all right? So I'll give you guys a couple of minutes. And if you have any issues, please let me know, and then we'll go through it together. And whoever has like an output already, please just let me know so that we can discuss it. So if anyone has like a result output, please let me know what value you get. Yep. Did you copy and paste it? I highly recommend just typing it out because oftentimes you get these white spaces. So try to type it out. Is it when you were trying to run MVCC?
Yeah.
Yeah. Yeah, just type it out. Did it work? Do you still have that error or?
I just need to load the quick one.
All right, gosh. Okay, has anyone been able to get the output or? 15? That's right. Yep, good. So, okay, great. You should get 15, all right? If you're not able to run it now, please try it later. But for interest of time, let's go through the program, like as to what's happening under the hood. So we start by the main function. So this is our host function, okay? So that's our host qualifier. And as I mentioned before, for the host qualifier, you don't really have to specify the host qualifier. It just is the main function. We specify A, B, and C, okay? And these are just the values that we initialize on the host, okay? And we create these pointers. So you have D_A, DB, and DC. And these are used later on to for the memory allocation. So these are the pointers that are used for the different functions that we look at. So CUDA malloc, essentially CUDA malloc, so this block here, you can think of it as like an error exception block. So CUDA malloc, it passes in DA. So what it does is it's checking that DA can be allocated with 1 byte of memory here. And CUDA success, so whenever you module load CUDA, these are some of the enums you get for free, okay? So please use this for your assignment. And the reason why it's very beneficial is because many times the common issue that people face when doing CUDA programming is that they oftentimes flip between the source data and the destination data in the function. And when you don't have these error exceptions, you just can't tell what's happening. It just gives you an error and you don't really know where it's happening. Whereas if you have this, you're not seeing what I'm seeing. Wait, sorry. So this is what I'm talking about. That block, it'll raise an exception as to they couldn't allocate whatever data that you had. So yeah.
Do you check size in this matrix? Is that anything or the actual amount of memory?
It could be anything, but normally the standard is like 1. Okay, yeah. Good question. So as we go down, so as I mentioned, you initialize the variables of the host, and then you have these pointers that you need. This is where the meat is. So with CUDA memcopy, we're specifying the destination, so where you want your data to go to. So you have D_A, &A, okay, which is your source, so the expected pointer. The size of just the int variable, which is the number of bytes you're going to copy over. Here you're using CUDA memcopy host to device. So in general CUDA programming, you're using 2 functions, host to device and device to host, and it's pretty self-explanatory. And upon that, you'll be copying memory. Okay, so you perform those 2 functions. And once you've done that, you launch your kernel. Okay, so when you launch your kernel, if you guys remember, we specified the grid dimension and the block dimension. So in this case, it's just 1 and 1. In reality, you're not going to ever use GPU programming to do a sum function. This is very trivial and very like overkill for like summing. Okay, but it's just an over example of how it works, just regarding the flow. So when we say grid dim, block dim 1 and 1, basically what we're doing is we launch 1 block per thread and then per block 1 thread. Okay, don't do this in real life. And as we go, we can look at the kernel function. All it does is it takes in the A, B, and C variables, and it just performs a sum. Very simple, okay? And you can think of it as, imagine if you have, this is 1 thread, but if you have hundreds of threads, you could perform that single kernel on all these threads simultaneously. So it's very quick. Once we've done that, so the kernel function runs, that's where you call the kernel in the host function. You perform CUDA memcopy, so it's the same as earlier, but the only difference is you're changing the destination. So once you sum A and B, you want to assign it to C, and then you're performing device to host because you were previously you were host to device, and then from the device, once you compute it, you want to bring it back to host. All right. So once you've done that, you'll be able to print the sum out. And then, as I said before, you always want to free the memory at the end. Okay, so never, don't forget that. And that's pretty much it for the function that you have. And into regards your Slurm function, sorry, your Slurm script, just make sure you specify your partition as GPU. Otherwise, it's pretty much the same. Okay, and I'll discuss more into regarding the homework as to how many threads you're specifying and etc. Any questions? Yeah.
You could have asked him something that's more than the size of one egg.
Yeah.
Into
Where?
Like
for your grid so your kernel function or?
Well, anywhere.
Oh.
You allocated
Yeah.
the size of an integer, right? So you try to pass it array of size 3 or 4 or really
No, it wouldn't complain. No. But it's just common practice just to use one like as like a is that your question as to if you could specify more than one?
I'm just trying to understand like when we're allocating memory from the device.
Yeah.
Are we just saying this like the variable needs some amount of memory, or is it like the specific amount of memory it needs?
Oh no, it's the former. So you're just saying that we're just allocating for this specific pointer one like byte of memory. That's it. Just checking. Yeah. Good question.
Going off that, so like
yeah.
copies, then you like if you copy like a double.
So could you repeat that?
So going off that, if you valid only like one edge, but you might copy like a double,
yeah,
no double.
Okay.
But if like overflow, if you something else.
So if you mem copy and then
double,
yes, that would raise an exception.
so, but it wouldn't overflow.
No, it would just be an exception. Yeah. Okay. All right, cool. So, sorry guys. All right. Before we proceed, there's some things about concurrency I want to discuss. So here's the thing. So we know that the host calls the kernel code, and it's really quick, right? It takes only like a couple microseconds. So we can deduce that launching the kernel is very cheap. It's a very cheap operation that you do. And one of the issues is that the host will continue to execute, and you should be aware of this when you think about concurrency. So say you launch a kernel and you don't really specify when it should end, and you want to print the value of C immediately, you actually will just get garbage output. You won't get anything legible. And in some scenarios, you wouldn't really care about this, but this is why CUDA kindly gives us CUDA device synchronize. So CUDA device synchronize, you can view as like a barrier, right? And so it basically tells us like, hey, don't go past this line in the code until all the kernels prior have finished, okay? And the beauty of it is that if you look at the code that I gave you, I didn't like specify any CUDA device synchronize, right? And the reason being that is because the copy function, so the copy operation actually acts as like a barrier, okay? So the copy operation will wait until the kernel to finish and the threads to settle. But you have to be careful about this because the more barriers that you have, the more random behavior you'll actually get. And so basically less barriers are better, but if you need a barrier and you don't have one, that's even worse. Okay, so try to minimize the barriers, but then be smart about what you're doing with it. So you might be asked, okay, so we have one kernel in this example. So what happens if you want to launch multiple kernels, right? That is fine. So in this case, you launch one kernel, you keep the CPU going. But if you launch a bunch of kernels in a for loop, that's still okay. One thing about it is that in CUDA, we have something called a CUDA stream. And what a CUDA stream is that essentially if you have, let's say 100 kernels running at the same time, and you dump it into one CUDA stream, what it does is it performs a FIFO action where the second kernel will only execute until the first kernel has finished running. So the benefit of that is it takes care of ordering for you. So let's say you have two different problems, problem A and problem B, separate problems. Problem A requires, let's say, 10 iterations, problem B, 11 iterations. You could actually dump those into the same kernel, same CUDA stream, and it will actually run, the ordering will be taken care of you from CUDA. Or you could have two different CUDA streams and then the ordering will be taken care of separately, okay? That's just a design choice and it really depends on the GPU hardware you're working with, okay? Any questions about that or, cool? Okay, so what is the challenge with kernels, right? Because everything seems pretty simple. You just have a kernel function, you can just run it on a thread. your problem is solved. So in a very trivial example, we looked at one block and one thread, okay? But in reality, when you're doing GPU programming, you're actually going to end up with hundreds and thousands of different threads running at the same time. So this is great, right? Because each thread could work on a single piece of data in a multi-dimensional data space. But given how many threads you have, how do you actually dictate which thread works on which piece of data? Okay. And so that's essentially what a kernel does. And most of the work comes in GPU programming actually comes from dictating which kernel does which part of the data and how dictating that action. Okay. So to solve this, we're given what we call a thread IDX, a thread index. Okay, so every thread will run code similar to NPI. Like when we look at NPI, right, for assignment 1, you had every thread running a program, and every thread is running that function in our case, which is a kernel. Okay, so how do we tell then which piece of data to work on? So we're given a thread IDX, and similar to NPI, where a processor has a specific ID, where you guys used. If we have like an ID and a processor, we just need to assign the processor a specific job to handle, right? So your problem is solved. So if you can specify which thread can do which job, why do we bother then with grouping these into blocks, right? Why do we care? If we know that each thread, where they are with respect to your problem using this IDX, why do we bother even, grouping them into these different data structures? Okay, and that really comes down to the GPU hardware you're working with. Okay, so this is a basic architecture of GPU hardware. So the GPU consists of several streaming multiprocessors that run all concurrently, and a bunch of these are existing in the GPUs. So you can think of it as multiple layers of these streaming multiprocessors. Okay, and each streaming multiprocessor contains multiple streaming processors within, which will run each one single thread. Okay, right. Are you guys following? And each single processor has a number of registers assigned to it, which is just local memory. And then any local variable created in the kernel are going to these registers. Okay. Any questions so far? Okay. So looking into this, so each streaming multiprocessor has some shared memory as specified. And all these threads are handled by one streaming multiprocessor and has access to a streaming multiprocessor. Sorry. Yeah, streaming multiprocessor, and you can control and set which of these which of these functions are running, and then all of these have access to shared memory. So it's much faster than access to global memory. Okay, so that's the benefit that you have. So all the threads aren't running independently; they're grouped into groups of 32. Has he talked about in class SIMD at all? Yeah. So you can think of it as like a SIMD fashion. All right. So when you step through a program, you have these blocks of 32 that step together, which inherently provides you some more optimization. And the core idea I want you guys to actually get from this is that you have access to shared memory. Okay, so similar data points can be grouped together and then could access each other. So if you have multiple kernels running and you have different variables specified in those kernels, each kernel within the same streaming multiprocessor can access each other very quickly through shared memory instead of having to access global memory, which is a huge advantage. Okay. All good? Okay. So why do we have blocks, right? So I've been going on about grids and blocks. So why do we care about it? So because you can put all the data into shared memory for easy access. So instead of having to go to global memory, and you have in shared memory, you can tell the GPU to take X amount of threads on the same multiprocessor, and then you can assign the data that are close to each other. Okay, so when you do that, you form a block, right? So the benefit of a block is that each multiprocessor could access different data types that are close to each other, so data variables. So in a block, you'll launch a bunch of blocks which consist of multiple threads that are specified, and this will be more clear in the examples that I give you in a bit. But you are guaranteed that a block will run on the same streaming multiprocessor because there's a limit of number of threads on each block, okay? Because each streaming multiprocessor can only handle so many threads each time. So I believe the block size is specified to 1024. So the maximum block size you have is 1024 threads. And you're guaranteed that the streaming processors running on each thread on the same streaming multiprocessor have access to the same shared memory, okay? So in that case, why do we, okay, I'll ask you guys this question then, okay? Why do we then want to group the threads into these blocks, right? With respect to the shared memory? Why?
So threads might be using the same sort of memory, and so they pass them to the end of the chat and share.
Yeah, exactly. So it removes you. So the streaming processor actually handles the data that are close to each other, right? That is allowed through access to shared memory, but also just provides you like this level of abstraction as to you don't have to really worry about the memory access because everything is on shared memory, right? So that's the main benefit of CUDA and very useful as you will see with your assignment. Okay, so okay, so just for recap, we have a bunch of these blocks and a bunch of threads in these blocks, okay? And we need to assign blocks to a chunk to a larger problem. So for instance, if I have a huge array, how do we know then, if you have a huge array, how do you know that a specific block is part of, like, what part of your array is this block working on, right? And so we need to specifically set that in CUDA. And we can't just use a thread IDX for using blocks because as you'll see later on, so these are four important terms I want you guys to really understand. It's thread IDX, so that's just the index thread of its block. Block IDX, which is just the index of the block dimension. That's just specifying how many threads are in each block, and that's used to situate the block in the bigger problem. And then you have grid dimension, which is just how many blocks are there. And so in reality, you know, the example that I gave you guys is just 1D block with a 1D grid, and that is fine, but you'll see that you can have multi-dimensional blocks and grids, and we'll see examples of as to how that works essentially. So let's go through one example. So here's a problem. It's a very, very trivial example. So let's say you have an array A, size 18 with some numbers. This is array A, and then we want to increment every value of A by 1. Okay, so what do you do initially? You initialize the variables, and you copy it onto the GPU, and using a 1D grid of size 6, right? 1, 2, 3, 4, 5, 6, 1D grid. You have a 1D block size of 3. So each of these are blocks, right? Size 3. Okay, and each of them have 3 threads inside, right? I want you guys to write a kernel that accomplishes what we incrementing. And the hint is that I want you guys to use the thread IDX, block IDX, as well as the block dimension. So I'll give you guys 5 minutes to create a solution. Yes. Okay. Okay, so wait, so your question is it better to have more blocks or more, like a bigger block size or bigger grid size?
Yeah, if you have a C5 video, it's better to ask like, now you have 6 blocks of video that you want.
Yeah.
It would be better to get it, is that preferable to having 3 blocks with time and each block?
Oh, so the short answer is it doesn't matter, but what matters is it depends on the GPU you're using. Okay, so some GPUs and it also depends on the problem that you're working on. So if there's a specific problem that is optimized for, like, let's say for getting features from an image, you might want to, you know, specify a different like dimension size for it. So it depends on the problem you're working on, the GPU. Yeah.
The size, how many
All right. Could anyone give me a possible solution for it? Both of you guys, yeah.
I think that it's A of block ID times block dimension plus thread ID.
Okay.
Plus or just plus 1.
Sure. Okay. Wait. Same. Yeah, that's right. So essentially, you'll just do block IDX dot X times block dimension plus the thread IDX, okay? And we can go through the example where, let's say, you start with this block, so you have block IDX is 0, okay? Thread IDX, let's say for this one is 0, and we have the block dimension that is 3. So in this case, you start with block IDX times block dimension, so 0 times 3 is 0. Then you plus the thread IDX, which is 0. So when you do that, you end up in the position index 0 of the array, okay? And imagine doing that simultaneously for each one. Then you can perform the sum at the same time, okay? So that's a very simple example. Now, what if, okay, so what if A was 2D, right? How would that affect the kernel, or would that even change anything? If you're passing in, a 2D data type to the kernel, how does that affect our kernel? Doing the same operation, right?
Couldn't you just make it like a 1D array?
Yeah, that's right. So in CUDA, like, it doesn't matter whatever dimension that you have, because from the kernel's point of view, it just flattens the array no matter what. So if you pass in a 2D, 3D, whatever, it's going to be flattened. And so you can just think of it as CUDA does not support 2D arrays in the sense that it's not double scriptable, right? But you might find online people on Stack Overflow saying like, oh, I found a way to pass in a 2D array and manipulate it. But if you look at the like certified answers, or if you look at the documentation itself, it's not supported. Also, if you try to work with the 2D array from the kernel's point of view, it actually defeats the whole purpose of CUDA, essentially. So the grid is describing the number of blocks. So essentially, no matter what dimension of like data type you're passing in, from the kernel point of view, it stays the same. So it just becomes a 1D array. Then you perform the operation the same way. Okay, so the kernel doesn't change. Any questions about that, or?
So you can pass in a 2D, go flat into 1D.
You flat into, so yeah, you pass in a 2D, you flatten into 1D. But the important part is that you need to copy the memory back into a 2D format. That's the important part.
I was going to just ask if the 2D comes back, if it didn't like it implicitly.
No. You have to explicitly specify the copy. So you want to copy it back onto the host as a 2D data type. Yes.
Does it deal with flattening?
Sorry?
Does it deal with flattening? So we pass it as a 1D type and pass it back as a 2D type?
It deals with the flattening, but you're gonna have to specify how you want to copy the data back. Sure. Yes. Okay. Just some more like going to more of the data type of the kernel. So as we mentioned before, blocks. So as you just saw, blocks and grids don't have to be 1D. So we're using what we call a DIM3 data type. So what a DIM3 data type is, it's just a tuple, like a 3D structure of X, Y, and Z. So if you want to create it, for instance, add 1, so 64 and 1024. So what this means is in your kernel function, each grid will have 64 blocks, okay? In your grid, 64 blocks, and each block will have 1024 threads, okay? Which are all one-dimensional. So if you have that scenario, then you just go from X of 0 to X of 1023. But you don't have to do it that way. That's just optional. You can even specify as 512, 512. It's a design choice and depends on the GPU hardware you're working with. But fundamentally, what I want to convey to you guys is that grids can be multidimensional also, okay? And you can adjust the tuple values as such. Yeah.
What is like the 1,1 represent?
Oh yeah, sure. So basically, in your actual program, you'll be specifying the grid size directly between these parentheses. All I want to show you guys is that even though the DIM3 data type has an X, Y, and Z coordinates, only your X value is changed. It's only X direction. Y and Z are always 1. Right? So I'm just breaking this part, showing that grid dim, block dim, even though they're X, Y, and Z, they're still going to be one-dimensional. Okay. Cool. So now, in a multi-dimensional grid, you'll be using a different set of calculations because we can't use the calculations that we had before, as it only goes through the X direction. And And we always deal with like flat arrays. So why do we even need 2D blocks, right? Like, why do we even care about 2D blocks? You know? So 2D blocks actually offers us more complex like conditional statements, as you can see. So we'll look at another example, okay? This time using a 2D grid specified as such. So let's say you have some array of size 18, some numbers as such. Like imagine there's an array, and we want to increment every value of A by 1, so similar as before, and you would copy it to the GPU. In this case, we're using a 2D grid size of 3 by 2. Okay, so this is your grid, 3 by 2. And then you have a 1D block size of 3, so 3 threads per block, so 1 by 2. And I want you guys to try to write a kernel for this 2D grid. Okay. So I'll give you guys 5 minutes and then go through the solution. So yeah, block dimension is 3, grid dimension is 3, and then grid dimension dot x is 3, and then grid dimension dot y is 2. Okay. Okay, you have a solution, just shout it out and then we can discuss. Yeah. Any ideas? It's okay if it's wrong. Just like give me your thought process as to how would you approach this problem, right?
So I guess you're gonna multiply the block index by the grid dimension on both axes, and then add the thread ID.
Right. So how'd you get the block index then?
Oh, I thought that was next.
So from here, how would you know that this specific block is block 0, for instance? How would you determine that? Because the CUDA doesn't know that, right? You have to let it you have to tell it like which block is doing which job regarding the bigger problem. So how would you know that this is block 0? Sorry? Grid dimension. Okay. Times 2. Okay. Why times 2? Because there's two arrays. Is it because there's 2 columns? Yeah, so because 2 columns, right? Yeah, that's right. So here's the kernel, but your intuition is correct. You have to first determine the block ID, but once you do that, then your thread ID just becomes the same calculation as before. And these answers will be posted on Canvas later. But essentially, we first calculate the block ID, which essentially tells us basically which block am I. And then we take the grid dimension. So the grid dimension, as you specified, is how many columns we have in the grid. In this case, is 2. All right. So if I'm block IDX is 0, and then block IDX dot x is 0 and block IDX dot y is 0, then I'm essentially block 0. Okay. And similarly, if my block IDX dot x is 0 and block IDX dot y is 1, then I'll be block 1. Okay, the next block. And then you repeat that operation. Is it this one? Yeah. No. Sorry. You repeat that operation for each block, so then it goes 0, 1, 2, 3, 4. Okay. So once you have the block ID, then it's pretty straightforward to calculate the rest. So once you know that everything stays the same, and we multiply the number of threads in each block. So why does this matter, right? I just gave you another example where you just determine the block ID, but then the thread ID calculation is the same as before, right? Regardless of being a 2D. So if you look at this another example, I think it'll be much more clear. So similarly, you have a 3x6 array of A numbers, right? And we flatten it to copy to the GPU. And using a 2D grid of 3x2 as before, I have 1D block of 3. Try to write a kernel that, one, increments the value of A by 1, but also if a value is on the first row of A, okay, so if you have A, if on the first row of A and the last column of A, you want to increment the value additionally by 1, okay? So try to perform that. Try to write the kernel for this, and the hint is just using an if statement, okay? But what the key is as to where you position the if statement in the kernel, okay? So, yeah, I'll give you guys a couple of minutes for that, like 1 minute, and then we can discuss the solution.
Yeah, so use changing doing that first line.
Moving on, can you specify the number of region?
Sorry, I can't hear, sorry.
Can you specify the number of threads we're using?
Yes, yeah, you explicitly specify the number of threads you use, yeah. All right, I guess because of time, let's just go through it together. So here's the kernel. So regarding block ID and thread ID, that stays the same. But the only difference is that, as I meant, if you look at the problem, the condition is that if a value is on the first row of A and last column of A, so in this condition, the first row of A is just block ID x when it's 0, right? First row. And then when block ID x is 1, right? When thread ID x is 2, that's going to specify the last column of the grid, okay? So once you do that, you just increment one more time, okay? And so why does this matter again? Well, the beauty of it is that if you are doing this in a 1D array, let's say just by using thread IDX, you won't be able to have these complex if conditions, because how else would you do this without an if condition, right? If you just have a one line, like what operator would you use? If you want to figure out the first row and the last column, like what operator could you use? Exactly. You'd use modulus. Now, modulus is notoriously slow on GPU. So that's why when you have a two-dimensional grid, it gives you the benefit of having a conditional statement to prevent like using a modulus operation that slows down your operations greatly. So just to sum everything up, we evaluate the usefulness essentially of a multi-dimensional block and grid because it offers you more like fast operations and prevents you from doing modulus operations. So in some cases, it's pointless to have a multi-dimensional grid, but in other cases, we saw that it isn't. And here's just a cheat sheet that I added. It just gives you like of all the different like thread indexing calculations that'll be quite helpful at a glance. And yeah, I guess if you're still unsure about how grids and blocks and what are the different, why we use these, just go through the discussion again, try to do the calculation by hand and try to understand it fully. And with regards to your homework also, okay? That'll be very helpful. So I guess that's pretty much it for CUDA. I included some additional like term definitions about what a thread was and what a thread block is, just a block of threads. You'll see this in the NVIDIA documentation, like a squiggly arrow. That's just how they represent their threads, like a squiggly arrow, okay? So when you see it, don't be alarmed, it's just a thread. Their way of showing a thread. Other than that, I really appreciate your time, guys. That's all for today. I'm happy to stay. Yeah, go ahead. Slow. Let's see. Yeah, I mean, I was gonna, there's a specific reason though. So modulus, okay, let me ask you, why don't you think it's slow? Like modulus itself is quite an expensive operation to do, right? So just a direct answer to your question is that the modulus itself, even outside of a GPU context, is a slow operation in programming, right? So that is exacerbated when you do it on GPU, especially when you imagine if you have 100 of functions that run modulus at the same time, that bottleneck is just going to increase exponentially. So you want to prevent that. Yeah.
So you have grids, and each grid has blocks.
Yeah. Yeah.
How does the work?
Oh, that's a very good question. That's I haven't covered this in the discussion because it's not really needed for the assignment, but I'm happy to discuss this after our discussion. Though.
You mentioned that on the slide.
No, I know. Because I had some slides hidden just regarding warp, and I'm actually going to make a Piazza post about it. That was my goal. So I'll add a Piazza post about warps and just general things you can look over the weekend. Just additional content. Yeah. Do you guys have any other questions about CUDA or like the final project or anything else? Assignment 4.
Final project question.
Okay. Yeah, sure. Go ahead.
I haven't taken a look at the spec yet, but.
Maybe you should.
Yesterday.
Yeah. So what's your question?
Do we need to use like higher dimensional grid for the assignments?
For the sensor calculation? I don't think it's needed. Yeah, but even if you do, like, how would that change the sensor calculation? I highly recommend just reading the assignment first.
Okay.
Then I'll be happy to answer any questions that you still have. Yeah, sure. Final project?
Yeah, so, you know, if we're getting denied proposals, I guess, what would be like the best direction